So now that we saw how to graph the 4 basic polar graphs, we're going to graph a little bit more intricate equations. So the first thing we're going to graph, which is going to be case 5, and I'll describe what it is after, is going to be r equals 6 sine theta. So this is different than case 4, because in case 4, it would have been the difference between this. 6 is equal to r sine theta, and r is equal to 6 sine theta. This was case 4. This is case 5. So they are different. So when r sine theta is on one side, then you can change it to y, and it's going to be a horizontal line. So be careful between the two, because they're similar, but one is r is equal to on one side. So the way I'm going to do this, and afterwards I'm going to show you some tricks on how to make it a little bit easier. But when you don't know how to graph something, you're going to create a table. And so I'm going to pick some points. I'm going to pick 0, pi over 6, pi over 2. I'm going to pick 7 pi over 6. Oh, actually, I want to pick pi. Hold on. Pi, 7 pi over 6, 3 pi over 2. So let's start to plot some points. We're going to plug that into our equation. So r is equal to 6 sine 0. Sine of 0 is 0, so 6 times 0 is 0. Then I have r is equal to 6 sine of pi over 6. The sine of pi over 6 is 1/2, so 6 times 1/2 is 3. Then I have r is equal to 6 sine pi over 2. The sine of pi over 2 is 1, so 6 times 1 is 6. Then here I have 6 sine of pi. The sine of pi is 0, so 6 times 0 is 0. Then here I have r is equal to 6 sine of 7 pi over 6. 7 pi over 6 is in quadrant 3, so it's going to be negative 1/2, which will give us a negative 3. And last but not least, 6 sine of 3 pi over 2. 3 pi over 2 is negative 1 for sine, so this is going to be negative 6. So I just plugged in, and I just evaluated sine, and then I found r. So now we're going to plot those points. So the first one is 0, 0. Okay, perfect. That's at the pole. Then I have pi over 6, which is right here. 3, 1, 2, 3. Positive 3, so I go forward. Then pi over 2 is 90 degrees, and I have 6. 1, 2, 3, 4, 5, 6. Then I have pi, and it's 0, so I already have that point. So I still have 0 pi. That's fine. Then I have 7 pi over 6, which is here. Negative 3, so I go backwards. 1, 2, 3. But I already have that point. It's this one. I already graphed it. So that was the multiple representations of points that we discussed earlier. And then I have 3 pi over 2, negative 6. So this is 3 pi over 2. But because I'm going backwards, I'm going to end up at the point I already have, which is right here. So something I'm going to show you after in terms of symmetry, because your function actually has sine in it, you're going to have y-axis symmetry. So that point at pi over 6 is actually going to mirror at 5 pi over 6. And I'm going to explain to you again after why. And that might be a little bit hard for you to see what this is going to be, which makes total sense. But this type, case 5, are going to be circles. And maybe you kind of figured it out by the name of the PDF. So here we have a circle. Perfect. I'm gonna make it a little thicker, and there it is. So let's kind of write what case 5 is in terms of general. So case 5 is going to be an equation that looks like r is equal to 2a, and I'm going to explain what the a is, sine theta, or r is equal to 2a cosine theta. Now, what does that 2a in the front mean? Well, it's going to tell you something about the center of the circle, and it's going to tell you something about the radius of the circle. So if your equation has sine in it, the center of the circle is going to be on the y-axis. So it's going to be 0, a. And if it's cosine, the a is going to go on the x-axis. So if it's a sine, the circle is on the y-axis. If it's cosine, the circle is on the x-axis. Your radius is always going to be the absolute value of a, because it could be negative. So a radius is a length, so it's always positive. So if I take a look at my equation, I'm going to actually take here, 6 in the front would be the 2a. So I would have 2a is equal to 6, which means that a is equal to 3. What that tells me is that the center of my circle is at 0, 3. This is the center of my circle. And then I have a radius of 3. So r equals 3, r is equal to 3. So we're going to see how we're going to use that, but before we do that, I'm going to do one more example of case 5. But before I do that, I want to take a pause and talk about symmetry, of how I was able to see that it had y-axis symmetry. So we have 3 different symmetry that we talk about when we discuss polar points. We have x-axis symmetry, which is the polar axis. We have origin symmetry, which is the pole. And we have y-axis symmetry, which is the angle theta equals pi over 2. And in each of them, I'm going to use the example I just graphed, which is 6 sine theta. And I already told you it had y-axis symmetry, and now I'm going to show you why that's true. So if you have y-axis symmetry, you can kind of see the diagram, right? So you have a point r theta. And if you have y-axis symmetry, that means that if you go clockwise with the angle, so instead of going counterclockwise, you go clockwise, the r will not change. So these points will be symmetrical to each other. So if you have x-axis symmetry, that means that you can take theta, make it into a negative theta, and it's going to be the exact same r. It's going to be the same equation. So let's put it to the test. So I have r is equal to 6 sine of negative theta. Because sine is odd, the negative goes in the front. So this is negative 6 sine theta. And then you compare, are these the same equation? The answer is no. It's 6 sine theta originally, and now it's negative 6 sine theta. So what happens here is that the test fails. It doesn't work. Okay, let's look at origin symmetry. So origin symmetry says that if you have a point r theta, you have to go across. But remember that going across means the r, you're going to go backwards instead of forward. So the r will be negative now. The angle was still the same, but you're just going to go backwards. So you will have origin symmetry if you can change the r's and the equation is the same. Okay, so let's do it with our example. So I have negative r is equal to 6 sine theta. I'll bring the negative over to the other side. I get r is equal to negative 6 sine theta. So then you ask, is this the original equation I started with? And the answer is no. So again, the test fails. Okay, the last symmetry, y-axis symmetry, and the reason I do it last is because it actually combines the x and the origin symmetry together. So you have a point r theta. What you would do first is bring it down. So first you would make the theta negative, and then you would go across. So now you would make the r negative. So in the end, they both end up being negative. So not only are you making the r negative, you're also making the theta negative. So let's try it. So I have negative r is equal to 6 sine of negative theta. This is negative r is equal to negative 6 sine theta. I'll bring the r to the other side, and I get r is equal to 6 sine theta. And then you ask, is this the original equation? And the answer is yes. So the test passes, and it has y-axis symmetry. Now, something I want to make a note of that's important. When the test fails, it doesn't mean that it won't have the symmetry always. It just meant that when you tested it, it failed, and you can't actually use it for when you're graphing. So it's never that the test will tell you for sure. The only way you're going to know for sure is when you graph it. So when it passes, it's good. But when it doesn't pass, then it just says that the test failed. Now, I'm going to let you use a little bit of a trick in this class that I'm okay with you using when you're graphing for time purposes, which is that if the equation has sine in it, it's going to have y-axis symmetry. And if the equation has cosine in it, it's going to have x-axis symmetry. Now, what does that mean for us? Let me move this down. That means that when you have y-axis symmetry, you're going to be able to graph here and then mirror everything over. So everything that's in quadrant 1 will mirror to quadrant 2, and everything in quadrant 4 will mirror to quadrant 3. And if you have x-axis symmetry, you can graph here, and then the quadrant 1 will mirror into quadrant 4, and the quadrant 2 will mirror into quadrant 3. So what you can do is use a mirroring effect, and I'm going to be doing this a lot while I'm graphing in polar. So let's take a look one more at case 5 before we move on to case 6. So we have r is equal to -4 cosine theta. So this is definitely case 5 because it's 2a cosine theta. So first I'm going to look at, so it's a circle. So the first thing I'm going to do is I'm going to take the 2a, and I'm going to look at what the 2a is. So the 2a is -4 in this case, which means that a is -2. So the center of my circle, because it's cosine, it's going to be on the x, so -2, 0. And the radius of the circle is going to be the absolute value of -2, which is 2. So I'm going to plot the center at -2, 0. And then I'm going to do the radius, so to the right 2 and to the left 2. And I'm going to put a little c here to remind me it's the center. Now, my symmetry, because it's cosine, I'm going to have x-axis symmetry. That means that I can graph in quadrants 1 and quadrant 2 and mirror down, so quadrant 3 and quadrant 4. Now, I can already see where my circle is going to be. My circle is going to be, I can see where the center is, and I can see where the endpoints are. So my circle is going to be in quadrants 2 and 3. So what I'm going to do is I'm going to pick an angle in quadrant 2 that's easy to evaluate for cosine, and then I'm going to mirror it down to quadrant 3. So a very easy angle for cosine is 2 pi over 3. This is also the reason why up here, when I was graphing sine, I only chose axis angles and denominators of 6. The reason I did that is because it gives me 1/2 and it doesn't give me radicals. So there was a purpose behind that. So here, the reason I'm choosing 2 pi over 3 is because cosine is a reference angle of pi over 3 there. So it's going to be 1/2 or -1/2. So when I plug it in, I get r is equal to -4 cosine of 2 pi over 3. Cosine 2 pi over 3 is negative because it's in quadrant 2 and it's 1/2 like we discussed, which makes this a +2. So then I can graph it. 2 pi over 3 is right here, 120 degrees, 1, 2. Now I'm going to mirror that point, and I'll do it in a different color, to 4 pi over 3. So it mirrors to 4 pi over 3. And now I can see like my circle a little bit better. So I'm going to come in, go wide, and here's my circle. So the center and the symmetry now, all of this information reduces that you don't have to do all that table anymore. So instead of doing all those points, what you can just do is recognize it's a circle, plot the center, recognize your symmetry, and then all I needed was one extra point, and that was it. Okay, next we're going to go into case 6. And I have 2 examples of case 6, and I'm going to write to you what is case 6 after we do it. So when we want to identify, for now it's going to be a question mark. The symmetry, it has sine, so it's going to be y-axis symmetry. What that means for me is that I'm going to graph in quadrants 1 and quadrants 4, and I'm going to mirror to 2 and 3. For sine, there's going to be 5 easy points that you can choose. Now, you can plot whatever points you want. This is just my advice for what you can use for sine that I think makes it really easy. So because I'm graphing from quadrants 1 and quadrants 4, I'm going to graph from -pi over 2 to pi over 2. So the points I'm going to use is -pi over 2, -pi over 6, 0, pi over 6, and pi over 2. So I'm going to graph -pi over 6, 0, and pi over 6. And again, the reason I'm choosing denominators of 6 and not denominators of 3 or 4 is because it makes sine 1/2 there. So it's easier. Okay, so when I plug it in, I get r is equal to 4 minus 4. The sine of -pi over 2 is -1. So this is going to give me 4 plus 4, which is going to give me 8. Then here I have r, 4 minus 4. The sine of -pi over 6 is -1/2. So this is 4 plus 2, which is 6. Then here I have 4 minus 4. The sine of 0 is 0, so this is 4 plus 0, or minus 0, which doesn't matter. Then here I have r is equal to 4 minus 4 times 1/2. So this is 4 minus 2, which is 2. And here I'm going to have 4 minus 4 times 1. 4 minus 4 is 0. So now I'm going to plot my points. So negative pi over 2, 8. 1, 2, 3, 4, 5, 6, 7, 8. Negative pi over 6, 6. 1, 2, 3, 4, 5, 6. 4, 1, 2, 3, 4. Then 2 pi over 6, 1, 2. And then 0 will always put you at the origin. Now what I'm going to do is I'm going to take those points and mirror them. So pi over 6 will mirror to 5 pi over 6. So 1, 2. Negative pi over 6 will mirror to 7 pi over 6. So 1, 2, 3, 4. Oops. Not 4, 6. 1, 2, 3, 4, 5, 6. Perfect. And then 0 will mirror to pi. 1, 2, 3, 4. And so that might look a little weird, right? Again, if you had never plotted it before, you would be like, what is it? So we're going to put it together, and then I'm going to show you. And I'm going to tell you the name of it, which is really cool. So you're going to make nice, fat, and it looks like a heart, a little bit of a heart, a little fat heart apple. And the name of it is actually called a cardioid. So it is called a cardioid. And it has the name heart in it. Cardio is the Latin root for heart. So it comes from that. So that's case 6. So let's write what case 6 is. So case 6 is r is equal to a plus or minus a sine theta. Or r is equal to a plus or minus a cosine theta. So the numbers have to be the same. So 4 and 4, and then the next one 3 and 3. That's what's going to make it a cardioid. And you will see in following videos what happens when the numbers are different. A little bit of a thing to help you. When it's sine, the fat part of the heart will be on the y-axis, which you can visually see on the one we drew. When it's cosine, the fat part will be on the x-axis. And then if it's minus, it's going to be on the negative. And if it's plus, it's going to be on the positive. So as you can see in the one we already graphed, because it was minus and it was sine, the fat part of it is on the negative y-axis. So when I graph the next one, the fat part of it is going to be on the positive x-axis. So now we can go through the motion here. Identify. It is a cardioid. Symmetry. It has x-axis symmetry because it's cosine, which means that I'm going to graph in quadrants 1 and quadrants 2 and mirror to 3 and 4. So just like I had 5 points that were easy to graph for sine, I have 5 points that are easy to graph for cosine. You don't have to use them. You can plot whatever points you want in quadrants 1 and 2. I just think this makes it easier. So I'm going to have 0, pi over 3, pi over 2, 2 pi over 3, and pi. So I'm going to graph 0, pi over 3, pi over 2, 2 pi over 3, and pi. And then I'll mirror. So you plug in. 3 plus 3, the cosine of 0 is 1. 3 plus 3 is 6. 3 plus 3, the cosine of pi over 3 is 1/2. So 3 times 1/2 is 1.5, so 4.5. 3 plus 3, the cosine of pi over 2 is 0. So 3 plus 0 is 3. 3 plus 3, now negative 1/2 because it's in quadrant 2. So 3 minus 1.5 is 1.5. And then 3 plus 3 times negative 1. 3 minus 3 is 0. Next we plot. So 1, 2, 3, 4, 5, 6. 4.5. 1, 2, 3, 4.5. 3, 1, 2, 3. 1.5. And then 0. So next, I'm going to mirror. So pi over 3 will mirror to negative pi over 3. So 1, 2, 3, 4.5. Pi over 2 will mirror to negative pi over 2. 1, 2, 3. Perfect. And then 2 pi over 3 will mirror to 4 pi over 3. So 1.5. So here's my cardioid. I can already see the shape of it. Remember to make it fat, right? It's not a line. It's like almost like a circle with an indent in it. So try to keep that in mind. Sometimes I see people making it really skinny. And there it is. And like we mentioned, I already knew it was going to be mostly on the positive x-axis, and then the points just made it accurate for me.